So let us begin by a short overview of what I'm going to teach in the part 2 of this course. So far in this course, you have seen and developed quantum field theory of spin zero particles. Now, clearly, that is not enough to describe the real world. So, in the real world, we see, particles, quantum particles of a higher spin, and their interactions. And, some of these particles are composites, such as protons or neutrons, and a lot of resonances that you see in particle physics, scattering experiment. And some of these particles are believed to be fundamental, unless you're a string theorist. Such as electron, quarks, photons, and things like that. So we clearly need to develop quantum field theory for these other kinds of particles. In fact, there's nothing really fundamental about quantum field theory. The modern point of view about quantum field theory is that it's the correct framework to describe the physics of interacting relativistic particles. So there's nothing sacred about quantum field theory. And, more and more, there's a lot of application of quantum field theory to condensed matter system. And in that case, those systems are not usually relativistic, and the degrees of freedom that they treat in that quantum field theories are emergent. They're not fundamental. So, in this course, for the rest of this course, we'll we'll develop the quantum field theory of, say, spin half particles and spin 1 particles with abelian gauge symmetry. So there is no need to take lecture notes unless you want to, because I will provide you with written lecture notes beforehand. There will be some group exercises. The explanation of those group exercises will be given in the lecture notes after the lecture, okay? Having said that, it may happen that the last couple of lectures, I might give you handwritten notes because my typing speed is not very fast. I'm still trying to catch up. All right? So a rough outline of the contents of the lectures are going to be something like this. So today we are going to talk about spinors as representations of the Lorentz group. In the next lecture, building on the work that we are going to do that, we are going to write down Lagrangians for the different kind of spinors. We are physicists, so we are interested in Lagrangians. We're interested in specific theories. So these 2 lectures will be largely classical. So I'll spend a lot of time on the classical representation theory of spinors. After having done that, we are going to quantize spinors, and we are going to see that quantizations of spinors will yield fermions. So fermions and the quantization of spinor fields. Since our aim is to do perturbation theory and in particle physics, we will then go and develop the Feynman rules. And also, before that, we're going to work out what the Feynman propagator is. For fermions, and then the fermion and the Feynman rules so for spinors, and for this we will use a particular theory known as the Yukawa theory. So all of this is we're going to be treating spin half particles. The Yukawa theory will have spin zero particles. So this will be a theory where spin half particles are interacting with each other by exchanging spin zero boson. So it'll be a theory of interacting spinors and scalar fields. So after that, we'll move up to describe spin 1 particles. So for that, we will do a covariant quantization of the electromagnetic field. And lastly, we'll try to bring all of this together and describe quantum electrodynamics, or QED, and cross-sections, and tree level, diagrams, and cross-sections. For a lot of you, this is probably not your first exposure to this subject, so I'm happy to answer questions, but I have to warn you that I will give precedence to more basic questions than some of the more deeper questions. We might have, if you have questions about the more foundational or advanced aspect of these subjects, we might have that conversation outside the class, okay? So a few notes on these lectures. So, my lecture notes will be more or less self-contained, but every lecture note will have some references, and you're highly encouraged to look at those references. You can always ask me which part of those references are relevant for the lecture, and I can let you know. Often during these lectures, I will say things like, "Oh, it can be shown," or or one can show, or it's easy to show. I strongly encourage you to fill in those omitted, to work out those steps. It's just not possible, given the time constraint, to do everything on the blackboard. But if you get stuck somewhere, come and talk to me, and we can, work that out, or I can help you. Also, at the end of every lecture, the handout that I'm going to give you, there are going to be a list of questions. And these are the interview questions which I think are coming out of that lecture note. So if you keep those interview questions in mind while you're reading the lecture note, it will help you a lot. And also, I encourage you to discuss those interview questions amongst yourself. And I will also have some interview question for practice during the tutorial. Okay? And lastly and not least, I am no expert on quantum field theory, so many of your basic and advanced questions may be left unanswered, but I will do my best, okay? Any questions? All right, so let's start. So why spinors? So why spinors? You might say, why not? Before even we, answer this question, there's even a more fundamental question we can ask. Why bother about representation theory? Why bother about scalars, vectors, tensors, spinors, and things like that? And the reason goes back to a theorem by Wigner. And Wigner showed that the symmetry of a physical system is realized as actions of some linear unitary operators acting on a Hilbert space that describes that quantum system. Okay, so there's a Wigner theorem from the early part of the 20th century where he showed that if you have a quantum system, so, symmetries of a quantum system realized as a unitary linear operators on the Hilbert space of this describing the system. Now, so this brings in group theory into physics in a big way. So this representation of the group of symmetry of your quantum system may be realized as an ordinary representation or a projective representation. And if you are interested in knowing more about this, I recommend Chapter 2 of Weinberg's book on quantum field theory, Volume 1. There's a nice readable discussion on that. So, given, so this is like the rough motivation for studying representation theory. Welcome, Carlos. So next, of course, we want to say, why spinors exactly? Why? And before we do that, let's just review the definition of what is a fermion and a boson. So can someone tell me what is the definition of a fermion?
That you have two fermions and you exchange them, their wave function changes by a minus sign.
Right. So two fermions are particles. If you take two identical fermions, their wave function is antisymmetric under the exchange of the two identical particles, right? And for bosons, the wave function is symmetric. And there's a so these define their statistics. And as a result of these statistics, fermions satisfy the Pauli exclusion principle, for example, whereas bosons have exotic states of matter such as Bose-Einstein condensations, right? Now, there's a theorem known as the spin statistics theorem. And which says, and I'm only coding the part that is relevant in 3+1 dimension, that fermions and respectively bosons belong to the half integer representation of the rotation group so in the case of non-relativistic quantum theory, half integer, since I'm integer for bosons. And for, or the Lorentz group, half integer representation of the Lorentz group in the case of relativistic system. Just as a side note, the spin statistics theorem admits more exotic particles statistics in lower dimensions, 2 + 1 dimension, and those are known as anyons. So this is the reason why we're interested in spinors, because we want them to describe fermions. And spinors are half integer representation of either the rotation group or the Lorentz group. Okay? So in today's lecture, we will see instances of both. As warm-up, we will describe spinors in non-relativistic quantum theory, and then we'll go on to describe spinors in relativistic quantum theory. Okay? So a little bit of waffle before we dive into the main subject. It's fun waffle. So spinors actually play a very important role in mathematics. And in some sense, I think spinors were discovered in mathematics before people realized their importance in physics. Clifford, for example, discovered Clifford algebra. Later on, it was rediscovered by Dirac, and we call it the Dirac algebra, something very closely related. As far as I know, spinors themselves were introduced by Cartan, who is kind of almost like a physicist as well, in physics, I think people like Pauli introduced spinors, and of course then Dirac introduced them in the context of relativistic physics. There's a field in mathematics called spin geometry, and it explores the relationship between spin structures, topology, and geometry of manifolds. So the idea of a spin structure is that you cannot have spinors on any manifold. That the manifold actually has to admit some kind of satisfy some topological conditions for it to admit a globally defined spinor field on it. So the field of spin geometry explores this. So the famous mathematician Sir Michael Atiyah, who has a Fields Medal as well, once said this about spinors: "No one fully understands spinors. Their algebra is formally understood, but their significance is mysterious. In some sense, they describe the square root of geometry. And just as understanding the square root of -1 took centuries, the same might be true for spinors." Incidentally, Michael Atiyah is famous for a theorem known as the Atiyah-Singer index theorem, where he actually found that for even-dimensional manifolds, the solutions of the Dirac equation, massless Dirac equation, something related to the number of solutions can be used as a topological invariant. So, he himself has used spinors to great extent. And in physics, spinors play a very important role in curved space-time. There's a whole field called supersymmetry, supergravity, where it describes the interaction of spinors and geometry. Spinors in curved spacetime can be used to reformulate physical questions. For example, in gravity, it was an important problem to prove that for asymptotically flat spacetime, you can define positive energy. And that's known as a positive energy theorem, and it was proved by Schoen and Yau. But later it was reformulated in terms of spinors by Witten, who basically said that, well, if spinors obviously exist in the real world, so what if we say, okay, we impose the condition that there must be, spinors must exist on asymptotically flat space-time, and from that he proved he proposed a new proof of the positive energy theorem. Anyway, these are not the avenues that we will pursue in this course, of course, but what my primary goal is to give you the tools such that you can build up theories of spinors. So the most basic tools, okay? So this will be a very pedestrian course, and please do interrupt me. So the lesson objectives for today's lectures are: first, we want to understand how spinors form a representation of the proper orthochronous Lorentz group SO1, 3 plus. Some people put the plus here. I don't know why I put the plus there. So the proper orthochronous Lorentz group is a subgroup of what you might call the Lorentz group. And remember, the Lorentz group are 4x4 matrices, which are orthogonal. But the proper orthochronous Lorentz group are the ones where the determinant of these matrices are 1, and their 0, 0 element is positive. So let me just remind you what lambdas are. Lambdas are the usual Lorentz group matrices, where eta is the metric of Minkowski spacetime written in Cartesian coordinates, okay? So the determinant 1 condition of the proper orthochronous Lorentz group, it ensures that we only consider those transformations which are continuously connected to the identity. Okay? So in the bigger Lorentz group, there are some discrete transformations such as time reversal and parity. And if you take those transformations, their determinant is not 1. So this means that we are only considering the identity element. And this condition ensures that the orientation of the time is not inverted by your Lorentz transformation. So if you have like a vector, like an interval, which is, say, future directed, you do not transform that to a past directed vector. So I think pictorially it's better. It's better to describe it as pictorially. So you have some point in Minkowski space, and there's the light cone going through it. And at this point says x, there's a point y in its future, right? So the Lorentz group will, the proper orthochronous Lorentz group will, if we apply it to this point y, it will keep it inside the future light cone. It will not flip it back into the past light cone, for example. Of course, if the point is outside the light cone of x, then of course there is no clear definition, notion of past and future. So we want to understand how spinors form the representation of the proper orthochronous Lorentz group. The second objective of our lesson is that we want to understand what are the different kinds of spinors. So for example, we are going to talk about Dirac spinors today, and also Wald spinors. So these are different kinds of different representation of SO1, 3 plus. And lastly, we are going to write down some explicit representations. So although I will start in an abstract way, at the end of the lecture, you will have very explicit 4x4 matrices for everything that we are going to talk about. And those are the representation that we are going to stick to for the rest of this course. And they're also very helpful representation of the spinor representation of the Lorentz group, because those are the representation that you will be using in your particle physics course, okay? All right, so let's do a little group exercise. So if you're sitting alone, I would encourage you, I would actually ask you to go and sit by some other human being. I know it's very annoying sometimes to be near another human being, but the exercise that I would like you to do is this. Say take two matrices, A plus and A minus, and A minus is the Hermitian conjugate of A plus. And suppose that A plus and A minus satisfy these anti-commutation relationships. So the anti-commutator of A plus and A minus is 1, but A plus anti-commutes with itself, and A minus anti-commutes with itself. In other words, A plus squares to 0, and A minus squares to 0 as well. So these are the properties of these matrices. Now, I'm going to ask you two questions. One is, consider the operator n, which is A plus A minus. So what are its eigenvalues? Okay. What are its eigenvalues? That's question number 1. And question number 2, probably a little bit more difficult, is, what is the dimensionality of the vector space on which A plus and A minus act? The minimum dimensionality, okay? So let me give you like 5 minutes. Think about it, and then discuss it amongst yourself, okay? Oh, let me give you hints. I like hints, don't you? N squared is equal to n. You can show this. Okay? Who wants to answer? Yes?
The first one is 0 and 1. It's eigenvalues.
0 and 1. Okay, very good.
The second one is 2.
2. Okay. Okay, so somebody answered that. The answer to the first question is 0 and 1. And that much is rather straightforward to see. So let's take this to be an eigenvector. We're not doing quantum mechanics here. We're just using the bracket notation as a vector space notation. So this is equals to this. Now, you can verify that the n squared is equal to n. So this will mean that if I apply this again, we have n squared, of course, of n. But since n squared is equal to n, we must have this equal to n squared equals to n. And so the possible eigenvalues are 0 and 1. Okay? So they're a little bit like fermions, right? Can either be occupied or not occupied. A little bit more work. You can show that the commutator of n with a plus and a minus acting on the state n is given by so, I mean, we can say, okay, maybe since there are two eigenvalues, maybe this whole, the vector space is just two-dimensional, right? So that much is obvious. But there could be some degeneracies and stuff like that, but in this case, there aren't. But the thing that I wanted to kind of point out is that you can look at this in analogy with the way that you construct the Hilbert space of the simple harmonic oscillator using, say, ladder operators. So the a plus and a minus can be thought of as creation operators and annihilation operators. And that comes out of this relationship because you can write this out and then so this is the n gets replaced by its eigenvalue. So n acting on this state is then so if the state n has eigenvalue n. So when you apply, say, a plus to this state, it increases the eigenvalue by 1. When you apply a minus to the state, it decreases the eigenvalue by 1. So this gives you the interpretation of a plus and a minus as raising and lowering operators. So if you take the 0 state, then applying a minus to it gives you 0. And then if you apply a plus to it, according to this formula, you should be getting the state 1. But because a plus squares to 0, if you apply a plus again to 1, you get 0. So there's an upper limit to the number of states you can get, unlike in the harmonic oscillator. Okay? And now if you take the state 1 and apply a minus to it, you go down to the 0 state. Okay? So by doing this, we can see that the basis states are just 0 and 1. Therefore, it's a two-dimensional vector space. So because it's a two-dimensional vector space, these matrices must be 2 by 2 matrices. So let me give you a representation of these matrices. So for example, this is a representation. And then So we do this problem because twice in this class, this algebraic structure will basically be important in what we have to say in working out the dimensionality of the spinors. So having done this, let's move on to non-relativistic spinors as a warm-up. So we want to develop the quantum field theory of relativistic spinors, but as warm-up, let's just go and revisit something that we know, but kind of reformulate it in this language, in a language that's going to be useful for us. So so you know in quantum mechanics, if you have a spin-half particle is described by a two-component wave function. Right? Now suppose you rotate that particle or the system which contains that particle, then you get some new wave function. And the new wave function is related to the old wave function by so you're rotating the particle by some angle theta around the z-axis. So this is what you get. So the half here is very important, because what this half means that if you rotate the particle by 2 pi, so if theta is 2 pi, then under this rotation, the wave function of the particle goes to minus itself. Okay? So as you know that these matrices are matrices from SU2. You know that from quantum mechanics. These are SU2 matrices. So the SU2 matrix, so they form a representation of the rotation group. Okay? A spinor representation of the rotation group. And the SU2 representation is generated by the Pauli matrices, and let's just familiarize ourselves with the Pauli matrices. Sigma 1, sigma 2. So the generators of SU2 are actually the Pauli matrices divided by 2, and that's where this half comes in. And using the properties of Pauli matrices, the Lie algebra of SU2 is given by this. Okay? This is the same Lie algebra as SO3 or the rotation group, okay? But if you take the rotation group, which is SO3, and take a vector and rotate it around some z-axis by 2 pi, you get the same vector back. You don't get the vector up to a minus sign. But in the case of SU2, if you take the spinor representation and you rotate the particle or the system by 2 pi, you get a minus sign. So this is like one of the hallmarks that distinguishes the spinor representation from other representations. Okay. So we all know that for spin-half particles, the wave function has 2 components. Now what I want to show you is that this is actually a result of this exercise that we did over here. It's the same thing in disguise. So to do that, the Pauli matrices satisfy these relationships. So this is nothing but the Lie algebra of SU2 written in terms of Pauli matrices. But the Pauli matrices also satisfy this anti-commutation relationship. Okay? And you can verify this very easily. So now let's take sigma 1 and 2 and construct these two operators. And they are Hermitian conjugate of each other. So sigma plus minus. Okay? Now you can use these relationships to show that sigma plus and sigma minus anticommute up to the identity operator. And the commutator of sigma 3 with sigma plus minus is plus minus 2 of sigma 3. So these two equations are analogous to the commutator that n has with a plus a minus, and also the first anticommutator up there. So what they mean is that sigma plus and sigma minus can be thought of as creation and annihilation operators, and they increase and decrease the eigenvalue of sigma 3 by 2. Right? And therefore, using that analysis, we can say that the representation of this algebra must be two-dimensional. So which brings us back to the familiar observation that in non-relativistic quantum mechanics, our spinor wave functions, our spin-half particles, are two-component vectors, two-component spinors. Okay? Do you see the connection? The 0 and 1 that we constructed here, if you create an arbitrary vector, it'll be a two-dimensional vector, right? And what I'm telling you is that the mathematical structure behind the fact that this is two-dimensional is exactly that. Of course, here everything was constant. You know, there was no space-time. In the case of quantum mechanics, you have to promote these guys to be functions of space-time, but the underlying mathematics is the same. Okay? The algebraic structure is the same. Okay, questions? So we can think of these sigmas, sigma plus minus, as fermionic raising and lowering operators. And why fermionic? Because the eigenvalues of sigma 3 is discrete. It has only two eigenvalues. In this case, the eigenvalues of sigma 3 is plus 1 and minus 1. But this is just same thing as having an eigenvalue of 0 and 1 in disguise.
Is the sigma 3 on the right-hand side should be sigma plus minus?
Yeah, thank you. Someone's paying attention. Yeah. All right. Okay, so this is our warm-up exercise. Now let's get to the real, the thing that we are interested in, which is relativistic spinors. And then In physics, this story goes back to Dirac. Dirac was married to Eugene Wigner's sister, so he had a Hungarian connection. When I was a poor graduate student in England, my landlords were Hungarian, and the husband was a mathematician, the wife was a very talented sculptor, and they were very good friends with Dirac. So they told me a lot of Dirac stories. Dirac had photographic memory, but he thought of it as a burden. So sometimes Dirac was known for his long walks. He would go around walking around Cambridge. Cambridge is very beautiful and very good for walking. But before he went on long walks, he would take his memory, put it on the windowsill. He had to play these games to kind of run away from the burden of having a photographic memory. All right, so relativistic spinors. So this comes from the Dirac equation. And the story of the Dirac equation is an amazingly beautiful story, I think. So this is a first-order differential equation. You probably all know how Dirac arrived at his equation, but I want to revisit the story anyway. So Dirac wanted to wanted to have a relativistic generalization of the Schrodinger equation. So he wanted like a relativistic generalization of the Schrodinger equation. And if you have forgotten what the Schrodinger equation is, it's something like this. I always forget. So we are using units where h bar is 1. Now the Schrodinger equation has a probabilistic interpretation, and Dirac wanted that. So if you take the Schrodinger equation, you can derive from it an equation of continuity. Right? So you can derive an equation which looks like this. So the rho is a positive definite quantity. And therefore, you can give a probabilistic interpretation to this equation. By the way, if you don't know, if you haven't like derived this equation from this one, have a go. It's a very short exercise. So the key to probabilistic interpretation is that rho is positive definite. But having this kind of density is related to the fact that the Schrodinger equation is first order in time. Before Dirac proposed his relativistic equation, there was another relativistic equation. It was the Klein-Gordon equation. And let me remind you what the Klein-Gordon equation is. I'm sure Dan has drummed it into your head by now. But the Klein-Gordon equation is relativistic, but it is second order in time. So, and you can derive, again, a continuity equation from this equation, just multiply it by psi star and manipulate stuff. But the density that you get in that equation is not positive definite. Therefore, the Klein-Gordon equation does not yield a probabilistic interpretation. So this is the motivation why Dirac wanted a first-order equation. Because it's relativistic, the time derivative and the space derivative, they're all first order. And these gammas, Dirac used alphas and betas. These gammas are coefficients whose properties are to be determined. And how did Dirac determine their properties? Well, he said that, the Klein-Gordon equation doesn't have a probability interpretation, but it has one thing going for it. And that is, if you take a plane wave solution of the Klein-Gordon equation, so you say, okay, let's consider a solution of the Klein-Gordon equation, which is of the form, say, e to the power minus I p dot x, where p is a 4 momentum vector, then the Klein-Gordon equation yields the correct energy momentum relativistic energy relationship. So the Klein-Gordon equation actually gives a square. So this is the 3 vector of the relativistic energy relationship. Okay? So Dirac said that, well, I require the solution to my equation to satisfy the Klein-Gordon equation. So he wanted psi also to be a solution to the Klein-Gordon equation. So the way he did that, he derived the Klein-Gordon equation from the Dirac equation by multiplying the Dirac equation by this operator plus m. He applied that to the Dirac equation. Now, let's write this as nu, summed over repeated indices. So then you can rewrite this as half of the anticommutator of gamma mu, gamma nu. Because this is symmetric, that's why you have a symmetric combination here. So this almost looks like the Klein-Gordon equation. So to get the Klein-Gordon equation, then Dirac had to impose this condition on the gammas. He said they must then be 2 eta mu nu. And that is how he derived what is now known as the Dirac algebra. Okay? Because this equation becomes the Klein-Gordon equation if the anticommutator of gamma mu nu is 2 eta mu nu. So this is the Dirac algebra. And I'm running behind, but that's okay. So let's now talk about the properties of the Dirac algebra. Eta mu nu is the inverse metric of the Minkowski space written in Cartesian coordinates. So it's our convention is mostly minus convention. Okay. Now, to figure out the dimensionality of the Dirac spinor, we have to now study this algebra. Let's do this over here. Right. So okay, let's start here. Why waste board space? So because of our choice of the mostly minus signature of space-time metric, it follows that this algebra tells you that if you take the gamma 0, the square of that is 1. So you can show that this implies that gamma 0 must be a Hermitian matrix. The gamma i's, which are the spatial components of gamma, squares to minus 1, which implies that gamma i's are anti-Hermitian matrices. Okay? This comes from the fact that, you know, the eigenvalues of these guys are real, the eigenvalues of these guys are imaginary. So to find out what the dimensions of these gammas are, let us construct some other gamma matrices. They call them capital gammas. And let's construct them by pairs. So gamma 0 plus minus is half small gamma 0 plus gamma 1. And gamma 1 plus minus is half I gamma 2 plus minus gamma 3. So then, from these properties of the small gammas, you can show that the capital gammas, if you take the Hermitian conjugate, you flip the plus and minus, so A is 0 or 1. And then using the Dirac algebra, you can derive the fact that gamma A plus and gamma B minus anticommute up to a delta, Kronecker delta. And if you had gamma plus and gamma B plus or minus, they anticommute. So by now, these guys should look familiar. What we have here is two pairs of fermionic creation and annihilation operators. Okay? Labeled by A. So we have, say, two pairs of fermionic creation and annihilation operators. So you'd expect that for each pair, you should get two vectors. So you would expect that this would give you a four-dimensional vector space. And indeed it does. So explicitly, what are the vectors that these guys act on? So let us define by 0, 0, the lowest weight vector, that is the vector which is annihilated by all the gamma A minuses. So this is basically, this is annihilated, let's just write it like this. Gamma A minus, so that's how this is for all A. Now we have two raising operators, gamma 0 plus and gamma 1 plus. So you can apply gamma 0 plus on this guy, and then you get this state, this vector. If you were to apply gamma 1 plus you get a different vector. But you can apply both of these guys because they anti-commute. So 0 plus, 1 plus. So this acting will give you 1 and 1. Now if you apply another raising operator, because of this thing, gamma plus squared is 0, right? So this thing implies that gamma 0 plus squared is 0. And or gamma 1 plus squared is also 0. So if you apply another raising operator, you kill that state. So these are the 4 linearly independent states you can have. Therefore, we have shown that the spinor representation of the Dirac algebra must be 4-dimensional. So this 4-dimensional spinor is usually written as psi. And it's got 4 components. Let me make a few comments. Because the vector space on which gammas act are 4-dimensional, the gamma matrices themselves must be 4 by 4-dimensional matrices. Okay? The dimensionality of space-time being 4 and the dimensionality of gamma matrices is a coincidence. Now, I leave it as an exercise for you to figure out that if you were living in space-time dimensions 2k, even dimensional space-time, but not necessarily 4, then the gamma matrices would be 2 to the power k times 2 to the power k dimensional matrices. Okay? You can just generalize this argument. Just pair up all the Dirac matrices, and then you can show this, okay? So the psi that we have constructed so far is just a constant, right? As a prelude to quantizing the spinor field, we promote psi to be a function of space-time. Okay? Just in the case of quantum mechanics, that's what we did with the wave function, right? So we are going to promote psi to be a function of space-time. So although we have used the Dirac bracket notation, nothing we have done so far is quantum mechanical.
Yeah.
Okay, rumbling. What are you guys rumbling about?
Oh. It looks like that means that the gamma matrices should be 16-dimensional, not 4-dimensional.
4 by 4 matrix.
K is 2 in the case when D is 4. So 2 to the power 2 is 4. So
4 by 4.
So okay, not times. Okay, 4. I'm sorry. You guys are so literal. That's sorry. Yeah. Yeah. No, that's good. Thank you. All right. So psi is the psi is so far a classical field. It is not a quantum mechanical wave function. Upon quantization, it'll become an operator. It will never have a wave function interpretation. Okay? All right. So we have derived the Dirac matrices, but is this actually a representation of the Lorentz group? Let's try to prove that. So in the notes, I have some waffle about the tensor and the spinor and the vector representation. I'm going to kind of kindly skip that unless you want me to talk about that. I just want to go to directly how the representation that this object is actually a representation of Lorentz algebra. I want to show you that. Okay?
I have a quick question.
Yeah.
How did you get the fact that gamma 0 squared is 1, the gamma 0 dagger is?
Oh, so yeah, so this comes from the fact that we have chosen this guy.
Yeah.
But then you said that okay, if this is if squares to 1, then its eigenvalues are +1 and -1. So it has real eigenvalues. So if a matrix has real eigenvalues, then it has to be Hermitian. And so the gamma i's have imaginary eigenvalues, plus I and minus I, and therefore they are anti-Hermitian. Okay? All right, so let's go and prove that this is actually related to the Lorentz group somehow. Okay, so I think you guys came across the Lorentz group in the front end course on Lie algebra and Lie groups, but some of you weren't in that course. For example, Lie Waterloo students. So let me just do a quick review of what the Lie algebra of the Lorentz group looks like. So as you know that the Lorentz group is composed of these matrices which keep this interval invariant. So if you take a Lorentz transformation, then your x goes to x prime, y goes to y prime, and the interval, but this interval remains invariant. So this means that this lambda matrices satisfy this relationship, and this is a generalization of the definition of the rotation group. The matrices in the rotation group satisfy this thing. So in the Lorentz group, you replace the identity matrix by the metric of space-time. So a typical element of the Lorentz group, so a typical element of the orthochronous proper Lorentz group look like this. Okay, so omega mu nu is a rank 2 antisymmetric tensor, and therefore it has 6 independent components. 3 of these components parameterize the rotation, and 3 of the components parameterize boosts. And correspondingly, M mu nu is also antisymmetric in its labels. This is a 4x4 matrix, because this is a 4x4 matrix. Sorry, this is, let's just not, let's say alpha beta here and alpha beta. And here we are taking the mu nu element of this, so we are taking the mu nu element of this guy, okay? So the M's are the generators of the Lorentz group. And again, there are 6 independent generators of the Lorentz group, corresponding to the 3 boosts and the 3 rotations. Okay. Now, if there's an explicit expression for the generators of the Lorentz group, And they're given by, I can never memorize this, so I have to look it up. So using this expression, you can verify that it's actually antisymmetric in alpha and beta. Now, you can use this to verify the Lie algebra of the Lorentz group. So the Lie algebra of this Lorentz group is something, I think, again, this was sheeted in your front-end course on Lie algebra and Lie groups. I usually always make a mistake here. Okay? So this is the Lie algebra of the Lorentz group. There is a more familiar form of this Lie algebra that's given in the notes. What we want to do here is that we want to say, we want to show that the way that spinors transform, that transformation matrices have the same Lie algebra as this Lie algebra. That's what we want to do. So let's make a conjecture about how the spinors should transform under a Lorentz transformation. So you do a Lorentz transformation. Now spinors don't have space-time indices. They have what is known as spinorial indices. As you saw, that the dimensionality of the spinor being 4 was an accident. It's a coincidence. So I'm going to use like early Latin indices to label spinor indices. So this goes from 1 to 4, not space-time 0 to 3. So we make the conjecture that under a Lorentz transformation, that the spinor field becomes this thing. So there is some 4 by 4 matrix acting on the spinor. And as usual, the space-time dependence of the field transforms in that way. And now the claim is this. The claim is this 4 by 4 matrix has this form. It is a function of our Lorentz transformation. So we have written it as S is a function of lambda. Recall that each Lorentz transformation is given by some parameters which tell you how much you have boosted and rotated. Those parameters are the small omegas. So we have to parameterize S by those same parameters. So we write that as, so we write the same parameters, but the generators of the spinor representation will not be M, because that's not the representation that we are looking for. Those M's act on space-time coordinates. So there is some other generator, which I will specify shortly, which I call sigma. And the claim now is that sigma, the generators of the spin representation of the Lorentz group, is given by the commutator of the Dirac matrices, not the anticommutator, the commutator. Okay? So what you want to do now is that you want to now take these guys and work out what the commutators are. And it's a long calculation, but you would find that this commutator gives you exactly this relationship, with the m's replaced by sigmas. And therefore, we have shown that the four-dimensional representation that we have built is a representation of the Lorentz group of the. Okay. So, like an intermediate step that is useful is to observe that the commutator of sigma and a gamma is actually given by this thing. And we will come back to this formula next time. So use this as an intermediate formula to show that this is actually gives you the Lorentz group, the Lorentz algebra. Okay, in the last few minutes, okay. Okay. So some comments are in order. The four-dimensional representation that we have constructed is known as the Dirac representation. So psi is the Dirac representation. The orthochronous proper Lorentz group is a non-compact group. So what this means is that there's a theorem in group theory which tells you that non-compact Lie groups do not have finite dimensional unitary representations. And this is reflected in the fact that, and this we'll see it next time, we are almost out of time today, that these matrices are not unitary matrices. Okay, these are 4x4 matrices, so it's a finite dimensional representation of a non-compact group, but they're not unitary matrices. But you might say, okay, we are doing quantum mechanics. Our representations should be unitary. Otherwise, we'll be in trouble. Inner products will not be positive, stuff like that. And the answer to that question is, do not worry. When we quantize our theory, these guys will become operators. So although they are four-dimensional and they're not acted upon by unitary matrices, when they become operators, they will act on an infinite dimensional Hilbert space, which will be the Hilbert space of particles and antiparticles, analogous to what you saw in Dan's part of the course. And that space, infinite dimensional Hilbert space, is a unitary representation of the Lorentz group. Okay? So it is not a problem that this is, that this is not a psi, not unitary. So the last question that I want to ask is, this representation that we've constructed, is it reducible? Okay? Is it reducible or is it irreducible? So to answer this question, we invoke Schur's lemma. So Schur's lemma says that So if a matrix commutes with all the matrices of a group, sorry, matrix of a irreducible representation, then that matrix is the identity matrix. Okay? So we're going to take Schur's lemma and flip it around. We're going to say, can we find a matrix which is not the identity matrix, but which commutes with all the S's? If we can find such a matrix, then the representation we have constructed is not irreducible. And the matrix that is going to do the job is called gamma 5. And it's defined. The first definition is so that we can have an arbitrary dimensional definition: mu, nu, rho, sigma, gamma rho, gamma nu. Sorry, gamma mu, gamma rho, sigma. And you can verify this is okay. So we will come back to gamma 5 next time, but gamma 5 has these properties. It anticommutes with all the Dirac matrices. Therefore, gamma 5 cannot be the identity matrix. Okay? Because if gamma 5 was the identity matrix, it would commute with everything. So this means that gamma 5 cannot be the identity matrix. So gamma 5. Number 2 is gamma 5 squares to 1. So its eigenvalues are +1 and -1. And that means that gamma 5 is a Hermitian matrix. Okay, let me stop there. And sorry we didn't get through all the material. We'll start where we left off next time. And but do you have any questions? All right. So next time we'll pick up where we left off, and we will show that the Dirac representation is actually not. Well, the Dirac representation is actually a reducible representation, and it's composed of two smaller representations known as the Weyl representation, and then we'll talk about Weyl spinors. Okay, so Weyl spinors are very exciting objects. The standard model is mostly made out of Weyl spinors. Okay. All right, thank you. And I will start on time, and I will finish on time.